So far in our list of examples of functions of two variables and the surfaces they generate, or the surfaces we imagine as their graphs, we just showed a function and then showed its graph and tried to draw some connections between the two. What if we tried to do the same kind of thing, start with a function, but try to visualize it without resorting to having a graph in front of us? And again, an exam scenario would be a perfect case where this would be what you have. You'd be given a formula, and you'd have to do some visualizations, or it would certainly help to be able to visualize what the graph looks like without having, or without being asked to do a detailed sketch, which some of us might not artistically be up to. Let's consider this example here. We've got f of xy equals y squared minus x squared. So notice this negative. So this is again not the parabolic bowl. This is not z equals x squared plus y squared bowl. That negative obviously plays an important, makes an important change in the function. Well, what can we ask ourselves? Well, one of the first things we had in our list was identifying when the z value or the function value is positive. Well, where is it positive? It's positive when y squared minus x squared is greater than 0. Well, that's when y squared is greater than x squared. Okay, so now we're just going to be thinking in terms of the two dimensions of the input, x and y, and have the surface above. So now we're looking down from below, or looking down from above. Z-axis out of page towards us. All right, so the z-axis is coming up out towards you. Well, where does this particular region in x and y get defined? Well, the squares are a bit complicated, but I think it's pretty clear to see that if x is bigger than y, or x is less than y rather, well, where does that happen? There's a boundary at y equals x. And so if x is less than y, that's certainly this region here. But it could also be, what else could it be? We have some sign issues here that we can tangle out. Let's just take a quick example. What if x was, x is less than y? This is x is much larger than y because the y is small. Let's go here. If we also went out to this side, x would be fairly small. X would be small and we square it, it becomes positive, but the y value would be larger. So in fact, we have a region like that, which corresponds to y is less, or negative y is less or greater than x. So the y value, when we flip its sign, sorry, let me get that right here. That's really the absolute values that I'm trying to get at here. I was trying to sneak up on it, but apparently I do not have that ability today. That's really what we're saying, because when we square root both sides of this and take both positive or negative, what matters is the magnitude. Y squared in magnitude is going to be bigger than x squared if y is bigger in magnitude or absolute value when x is smaller in absolute value. And that turns into these two regions here. So this is going to be positive z values, positive z values. And where is it negative? Well, it's going to be the opposite case when the absolute value of y is less than the absolute value of x. Again, taking a look at the original function, well, yeah, if x is really big, or certainly bigger than y is, then x squared is going to be bigger than y squared. Take the difference, I get something negative. And last but not least, where is it going to be 0? Well, right across the boundary lines along y equals x and y equals negative x. Those are going to be the 0 levels for the function. So we already have some sense of what's going on here. If I imagine looking down from above, I have a slope coming out of the page towards me, going down into the page, into negative z values in the green regions, and coming up out of the page, as we move to the right. Again, this is an exercise in imagination more than detailed sketching, so try to imagine that you're looking down from above, the surface is peeling away from you I'm getting my signs all mixed up. Positive z means coming towards you. Positive z means coming towards you, and negative z means going away from you if you're looking at the xy plane with z positive coming towards you out of the plane. All right, so there's fairly limited amount that we can learn from that here. Let's take a look at some other things that we can do. We can do this by selecting sample values for x, y, or z and graphing the resulting one variable function. So we're just going to slice this. There's another way to think of this. Slice up the surface by picking x, y, or z values. All right, so let's set x to a constant. Well, that turns our, let's let x equal k. That's going to turn our function into y squared minus k squared. So if we try to sketch that out here, so now be very careful with labeling your axes. All those years of being trained to label your axes, this would be the wrong label, is going to come and bear fruit right now. We've let x equal some constant, and so we can, it's nice to change it and pick a value like k, because then it becomes more obvious. Here's the relationship. Z is related to y if I fix my x value. And if that's the case, well, what can we draw? If k was 0, we'd have the simple parabola. Let's do it here and here, here and here. So this line here corresponds to k equals 0 or x equals 0. So if we think of the x-axis coming out towards us here, then this would be exactly where it's supposed to be on a perspective drawing. It's exactly at the board or at the page, and we would see a parabola if we cut through the surface there. If we had k equals 1, then we would be subtracting 1. Well, what would that look like? It'd be the same graph, just shifted down by 1 everywhere, like so. K equals 1. And if we had k equals 2, we'd see it shift down quite a bit. It'd be minus 4, so it'd be down here. And it's also worth noting that those would apply as well if my x values were positive or negative. Here we go. And what I'd like you to do is try to imagine these shapes either in front of, that's positive x's. Oops. For positive x values, they're in front of the page or behind negative x's, the page. So this x equals 0 is at the page, and then we move out towards you, and then we see a lower shape, same basic contour, same basic profile, but move down, and then we see it moving down away as we move out of the page. These parabolas, we'd have a marching series of parabolas moving down with respect to one another. Also, because k equals 4 here, I'm sorry, k equals 2, or negative 2, which corresponds to x equals 2 or negative 2, we have these parabolas also moving back away from us. So we have a highest parabola at x equals 0, then as we move backwards through the page, we'd see those parabolas move down and move down further still. Take some practice. Try it again if it's not immediately obvious and see if you can visualize that. We'll show the detailed surface picture in a second. Let's flip that around and do the same kind of analysis with the y value set to a constant. So in that case, we had z equals, let's pick a different, let's call it c squared minus x squared. And in this case, now we would label that axis x and z. And we're asking, well, what happens as we change this value here? Well, we know that these are parabolas that open downwards. And this constant is going to play a role very similar to the last example. I'll go a little more quickly this time. So we have our generic parabola here. That's not really high enough. That's not. I'm missing the coordinate. We're close enough. This would be our c equals 0 or y equals 0. C equals 0 or y equals 0. And then if we made that 1, that would correspond to y equals 1 or negative 1. And that would be shifted up. So we'd have the same basic shape, just moved up. And like we saw before, 4, that would be y equals 2 or negative 2. We'd have a parabola like so. Now, the way to think about this is you're looking at the side, it's a side view of the function. So here we'd see parabolas that open down, and then as we move either deeper into the page or back out of the page, we'd have downwards open parabolas that are shifted upwards as we go. All right, still with me? I'm going to leave the Z actually as an exercise for you, because I think it's important at this stage to see the picture to reinforce what we're seeing already. I'll come back to the Z in a second. Let's label our axes here. We've got X, Y, and Z. This saddle shape is the surface that we obtain when we graph the function Z equals y squared minus x squared. And we can see those parabolas in the YZ plane that are open upwards and that shift downwards as we move out of the page or move into the page. When we talk about the direction, the XZ direction, we had downwards parabolas that went up as we moved in or out of the Y direction. And the Z's are a little less intuitive, so I'll leave those as an exercise. But what we end up, or what are called hyperbolas there, and those would be lines that have constant Z value. So one important note is that these blue lines represent graphs with constant X, Y, or Z values on the surface. We're going to return to that idea of slices, and in particular we're going to return to the idea of lines where the Z value is the same, all the points that share a same height, and we're going to use that extensively when we talk about contour diagrams in the next unit. But for now it's enough to see, okay, there's a way that we can at least start to imagine a surface without being able to draw a full sketch like this, simply by looking at what happens along lines of constant X value or along lines of constant Y value. And that is one tool in our arsenal for understanding the much richer field of multivariate functions. Obviously this is far more complicated than we could ever obtain in our old world with single input functions.